Hi, the project is Simulation Framework for STBC based MIMO system. With mobile devices becoming prominent in everyday life of people, the need for development in wireless communication has been exponentially growing. Few of the examples of wireless technology are wireless LANs, Wi-Fi, etc. However, limited bandwidth is a huge bottleneck in the data transfer and demands extensive research to meet the ever-growing data consumption rate. These reasons play a major role in driving the research community to cooperate and contribute to the wireless communication networks field. One particular domain in wireless communication is usage of multiple input, multiple output links. To perform beamforming, space-time coding, and spatial multiplexing, multiple antennas that allow MIMO systems are used. Receiver signal can be maximized over the transmit antennas by sending the signal with various weights and gains. Such technique of using variable phase and gain is called beamforming. Using variable phase is called beamforming. Many forms such as spatial multiplexing, diversity have their own advantages and disadvantages in increasing the network capacity or bandwidth. However, this paper majorly focuses on space-time block coding (STBC) and its variant. The work studies MIMO techniques to achieve longer range for transmission or data rates. The MIMO techniques enables the wireless transmission system to achieve higher data rate over long range transmission. For this, various STBC schemes employed for MIMO systems are studied. Alamoto's scheme for orthogonal STBC for 2, 3 and 4 antennas are well studied through MATLAB simulations and analysis. The major component of a MIMO system is a receiver Rx and transmitter Tx and channel H and forms the crux elements of an MIMO. NR and NT represents the total number of antennas in the receiver and the transmitter respectively. It can be seen that the system is represented by channels from the block diagram of the system. To take an example, the input of channel Tx has many inputs at its output, and in the same fashion the output of the Rx has as many as output at its input. There are two channel modes in which the system model is designed. Based on the modeling environment and accuracy, the channel modes can be simple or complex. The channels can be modeled by calculating the channel matrix according to physical representation of the environment, which would depend on the angle of departure, angle of arrival, and angle of time. And this model can be very complex. This method is demonstrated by Molish along with providing parameters for both macro and micro environment. These cells can also be modeled analytically, and in which case all channels in between transmit and receive antennas are considered as SISO channels and also considered to be independently identical and distributed. It is a fact that these channels could have spatial correlation and in between the links, and a channel with a particular correlation matrix can be formed. These matrices are typically measured in field and is bound to elements like antenna patterns and spacing between antennas and the surrounding reflectors. The major goal of the paper is to compare performance of different space-time block coding scheme, and the model is selected in a manner such that the correlation doesn't interfere with the performance. The two models for the cases, the case of line of sight and the case of non-line of sight, are discussed in this research. NLOS is non-line of sight. Rayleigh is the common model for research NLOS scenarios. It is applied to environments with plenty of scatters, and this model is independently identical and distributed, commonly known as IID, has unit variance channel elements, and zero mean is given by the formula as shown here. The LOS environment, a rank 1 matrix, and an HNLOS correspond to loss and N-loss respectively. Power contributed by LOS is referred to as P loss, while that of LOS is referred to as PNL loss. The HNLOS component is usually modeled as shown in the formula. A smaller fade margin is required for greater K factor in case of SISO systems, and for greater K factor HLOS will be more dominant and HNLOS will be less dominant in case of MIMO systems. But it has been proven via experimentation that LOS does not dominate often. Space-time block coding. Spatial diversity can be used in MIMO systems to fight fading in the channel, and this can be done via transmission of multiple imitations of same information via each channel, and this ensures the probability of information loss drops exponentially. MIMO systems antenna could be used to transmit a SISO system as the target rate is that of the latter system. The count of the independent signal reception marks the diversity order or the diversity gain of a MIMO system. A system with NR antennas to receive and NT antennas to transmit has complete diversity gain equal to NT-NR. A STVC encoding a single stream through the space making use of all transmit antennas and through time sending a symbol at a time is used to generate the replicas, and this is known as space-time coding. Space-time block codes have been widely used because they are fairly simple to decode. We shall see the various STBC techniques in the coming segment. Alamoto's STBC research named Alamotti came up with the very first scheme of STBC focused on transmit diversity owing to its simple nature and structure. It falls under both WCDMA and CDMA 2000 standards, and it achieves a maximum diversity of order 2NR, making use of two transmitters and NR receive antennas. It transmits two symbols every two time intervals and hence has a rate of 1. Now we shall look into both the antennas and its decoding method for scenario of NR receive antennas. The next method is orthogonal spacetime block codes. The equations shown in the paper indicates the block codes and the metrics for decoding. These equations were used for simulation and analysis purposes. Simulations. We have used MATLAB for simulation framework and derive conclusions out of it. Simulation framework is developed in MATLAB by leveraging Rayleigh model as described in the introduction. We simulate G2, G3, G4, H3 and H4 for the case of n equal to 1 up to n equal to 4. We modulate using BPSK, QPSK, 4QAM, 16QAM and 64QAM gray mapping constellations. Blocks of 100 symbols are simulated till 105-bit errors are generated. When SNR reaches 40 dB, the simulation is stopped. Another criteria to stop the simulation is when 100 blocks are simulated without any errors. The confidence level of 99.9% is achieved for BER of 107 with 100 errors. Results and analysis. All the variables are kept the same. The result for QPSK and BPSK is observed to be very identical, and hence BPSK is omitted while retaining QPSK for analysis purposes. Further, the performance can assume to be identical since the data for both BPSK and QPSK is identical. In this paper, the performance is studied and discussed for different block code and analyzed for various performance for NR and T, diversity order and rate. The image shows the result for simulation when NR is kept constant to 1. We can observe that for different code blocks, more bits are transmitted, the performance degrades. The performance variation is in the order of H4, G3, H3 and G2. But G3 outperforms H4 for low SNR even though H4 has greater gain. For low SNR, the performance is as follows: G4, G3, H4, H3 and G2. This figure shows the results for the case when NR equal to 4. For a particular modulation parameter value, it can be observed that the performance varies in the order of G4, G3, H4, H3 and G2. It was noted that the similar pattern is found when low SNR at NR equal to 1, where G3 is greater than H4 is greater than H3, having higher gain. On analyzing, we could conclude that the possible reason for the observed performance of achieving higher EBR for a given SNR is that at higher rate of H4, the H4 causes lower channel gain per symbol. This figure shows the variation of BER for varying NR between 1 and 4 while keeping the NT constant. Conclusions. In this paper, I first introduced the fundamental concepts, the advantages and the applications of MIMO. Further, MIMO modelings were discussed. Alameda's scheme was presented by introducing space-time coding. I further made a literature review on different code schemes for various code rate for different cases of transmission antennas. The algorithms for decoding and encoding of transmitters were both discussed. Simulation results were then presented. From graphs presented in the results section shows that the performance does not have a direct relation to diversity gain. This conclusion can be derived from the graph that G3 outperforms H4 for SNR and different NR values. Also, if the diversity gain are equal, the performance may necessarily not be equal. This conclusion can be derived from the graph that even though diversity gain is equal, G3 outperforms all. It was also observed that with multiple transmitter antennas, the power per antenna is significantly reduced. The interesting takeaway point from the research is that G3 and G4 outperforms H3 and H4, even though H3 and H4 have higher rates. Finally, I conclude that G3 and G4 can be performed and preferred, and also high code rate with lower order can be preferred rather than low code rate with higher order. Thank you. The MATLAB code models the spacetime coding techniques of MIMO based on different coding modules and equations. So for varying number of receivers in the MIMO model, the block error rate is measured for the varying signal to noise ratio, and the results are stored in an external file which has all the values for varying number of MIMO models. So each of the file has the number of receivers and transmitters and the block error rate. So as the file suggests, the functions are modeled based on the equations shown in the report, and on running the code, these functions are called. At the end of the simulation, we could use the plot everything script, which uses the external files, and plot a graph of BER versus signal to noise ratio, so which can be seen in the following graph. So for the analysis for different G and H's for the different QPSK, QAM and techniques, the graphs can be observed. The analysis can be found in the report. Thank you.